Section 2 gets into the graphs of polynomial functions, specifically polynomial functions that have larger degrees. And what we want to do in this section is review the different concepts to find zeros and then being able to quickly graph these higher degree polynomial functions. So the first thing we're going to look at is how do we draw a quick sketch based off of patterns of end behavior and multiplicity. And then secondly, we want to figure out the original polynomial function if we're given zero values. So there are a couple things that we want to look at. 4 characteristics that describe some of these polynomial functions. The first thing is what a polynomial function is in general. The first thing is that a polynomial function is continuous. The term continuous means that there are no holes or asymptotes, no piecewise functions, no gaps. In other words, I can draw a polynomial function without picking up my pen or pencil. No holes, no asymptotes. Second thing, for polynomial functions, we're going to have the same patterns as we did for our parabolas and our cubic functions and any other function that we look at in terms of how it relates to the parent function. So we want to look at horizontal and vertical shifts. We want to talk about stretches and shrinks. And we want to talk about x and y axis reflections. So just as we look right here, we've got horizontal is the inside piece of the function and its opposite. Vertical is outside the function. Constants larger than 1 will make the graph skinnier, and constants between 0 and 1 will make it wider. So as we look at the first one right here, just talking through some of the things that we see, we've got a polynomial raised to the 6th degree. And if I go through and look at the different pieces, this x minus 5 inside the parentheses indicates my horizontal shift. And this right here is going to be 5 units to the right. Remember, it's the opposite. It's on the inside. So here we're going to have 5 units right when we compare it to the polynomial function. We're going to be 2 units up. This 3/2 in front indicates we are going to be skinnier, and the reason is because 3/2 is greater than 1, and anything greater than 1 gets skinnier. And then we're going to have an x-axis reflection because of this minus sign. That minus sign could be pulled in front, which gives me an x-axis reflection. Second one's a little bit more complex. We're looking at a 5th degree polynomial. And I want to be careful about my horizontal shift here. I see the 4 inside the parentheses. My natural inclination is that I'm going to be 4 units to the left, because we've always said that it's the opposite of what is inside those parentheses. The one issue, though, is that this is a negative x. And that negative in front of the x when it's inside the parentheses indicates a y-axis reflection. So first of all, we've got a y-axis reflection. Then after that, I think, okay, if that was actually 4 units to the left, and then I reflect across the y-axis, where am I really? So just as a quick visual here, if originally my graph was shifted over here, say 4 units to the left, and then I've got a y-axis reflection, it ends up being over here, since this is my y-axis that I'm creating the mirror image around. So really, if I were to look at this function, this one's going to be 4 units to the right. So it's not to the left there because of that y-axis reflection. The end result is that my function was shifted 4 units to the right. The 8 units up don't change. And then we've got a wider graph, because the 1/2 is between 0 and 1. And when 1/2 is between 0 and 1, or when any value is between 0 and 1, that's where we have the wider transformation. The third point we want to look at is the leading coefficient test. And the leading coefficient test is going to give us the end behavior of the function. So here's two facts. When the exponent is odd, it will rise and fall in two separate directions. So I'm going to either have the idea of up down or down up. And then when the exponent is even, it will rise and fall in the same direction, which is going to be up up or down down. So the first one right here that we've got, 2x to the fourth minus 5x cubed plus 6. We've got an x to the fourth, which is an even exponent, and the 2 in front is going to be positive. So what that tells us is our graph in the end, we're not quite sure of all the behavior in the middle, but it's going to be up and up. There's going to be something there in the middle, but we know the end behavior is going to be up and up. If we have an even positive leading coefficient, that's when it's up and up. If we have an even negative coefficient, that's when it's down and down. And when we talk about leading coefficients, we've got to make sure our powers are in descending order. So we are actually looking for the largest exponent. The second one that we've got here, negative 3x to the fifth plus 999. This one we've got an odd exponent for a leading coefficient, and we've got a negative. So that one's actually going to start up and then go down. So we're going to have something that looks like that. We don't know what's happening in the middle, but we know the end behavior is up and then down. So if we look at an odd but positive leading coefficient, the pattern is going to be down and up. So the one on the far left would be down, the one on the far right would be up. If it's odd and negative, then it's going to be up and down. And then the last point we want to make on this section is the term zero value, solution, factor, x-intercept are all tied together. This is all describing where the graph crosses the x-axis. And you can see right here, there's many different ways that we can do it. Factoring, graphing, quadratic formula, the stuff we did in the previous section. But the question that we want to ask is, how do we convert a zero value to a factor? So if I were to know a solution, or a zero value is x equals negative 3, how do I make that a factor? And the way you make that a factor is you make the right-hand side equal to 0. So if this has to be equal to 0, I've got to move the 3 to the other side, which means x plus 3 is equal to 0, which then the factor that you're used to seeing would be x plus 3. If I had x equals, say, 5/6, I would do the same approach, that I need to get everything on one side and then 0 on the right-hand side. So if I were to convert this guy, I could just subtract over the 5/6. We'll say x minus 5/6 is equal to 0. Or if you don't like fractions, you can do your algebraic simplification here. X equals 5/6 is the same thing as 6x equals 5 when you multiply both sides by 6. Then, in order to set this equation equal to 0, you would say 6x minus 5 is equal to 0. So there's maybe another factor you're more comfortable with. So either way is correct, but knowing how to convert a 0 to a factor is going to be key in this section.